So this agenda, a little bit overview of my company, and then the technology we have, why it matters, and then we serve a lot of government projects and what they require. So we look for partnership here for new technology needed, and also target use case, some military, some more like AI communication. So company started as a chip design company. Our background was in laser driver, so we made laser driver for DVD recorder many years ago. And then we switched to LED driver. Essentially, right now we are a display company based on our driver technology. We don't sell a driver, but sell a display. Lots of display here in. So we got display here near Harvard in Harvard Business School. We also have a big screen in Microsoft in their London store. Yeah, many public venue you can see our display in the Lincoln Center. Yeah, lots of customer, government, big corporate. Yep. So that's our company background. So our specialty is actually really the driving, the LED. So I think there's some problem probably MicroLED people don't realize that, but eventually probably you're going to realize when you go into production. So like RGB need to be driven by different voltage. If it's same voltage, could probably too much power consumption on the right LED. If it's not QD display. And also LED need to be protected properly. So should not have any like crosstalk between pixels. So how to isolate that pixel properly? It's difficult task. We have the technology we call LISA, LED and silicon array, and the technology to do that. And there's another thing we call it ZAG. Actually, it's also very interesting topic. We talk about like LED. We always talk about wavelengths, efficiency, and threshold voltage. But one parameter you guys may not understand is the impedance. Actually, each LED has different impedance. If you use different same current drives, different LED, you will end up different color or brightness, especially in low brightness area. So LED has a very high dynamic range. You can go to 16-bit grayscale easily. But if you don't compensate impedance well, you probably only can go to that 10-bit. So the last 6-bit is really low grayscale compensation, actually fighting with impedance variation. So we spend a lot of time developing the technology, and it's perfectly tuned and work. The other thing is called communication protocol, right? So if you drive LED from HDMI all the way to the LED, you may need a lot of frame buffering, right? So frame buffer causes the delay. Frame delay also costs higher, lower power consumption, higher power consumption and low latency. So we come up a method to do the communication without the frame buffering. The fifth technology we talk about called promises technology, which I think also important because LED can switch in very fast, like increment at 1 nanosecond pulse for each LED, right? So if you deliver that means 1 gigahertz switching for each LED, there'll be tremendous power consumption. So we come up a method to drive LED by phase, not by the clock. Actually, our clock running much slower than the needed clock speed. Yeah, and then the scramble progress gain is kind of an integration of all of that to what MicroLED communication application. So basically, SiliconCore, our technology is basically end-to-end video custody from the video input all the way to LED, taking care of communication problem, reduce power consumption, and take care of all the LED parasitic problem it has. So it has been all these things applicable to mini LED, but also applicable to micro LED down in the future. So we have been working with U.S. government quite a few years now, since 2022. We got award from the Air Force and Navy and Army as well every year. So we are applying LED display technology for the government. So U.S. Air Force, we have a secure display for them. It's deployed in Alaska, and we have Navy develop IR simulation for pilot. And then we also recently won a mission center large screen display for vessels, hopefully for all the vessels for U.S. Navy going forward. So yeah, I got an award. We got an award called Defense Business Acceleration, Microelectronic Challenge 2023. Over 200 companies competed, and we were number 2nd. We were number 2 in the nation. So we got an award to develop the IR-driven IR display for the simulation and training. So let's talk about micro-LED development. I'm not talking about AR, VR. I think there's a lot of application not related to AR, VR at all, but need micro-LED. So this is kind of like not exactly talking about TFT or silicon-based. It's just traditional PCB-based, right? We think we waited for so long for the TFT-based micro-LED. There's so much dead pixels, right? For whoever did it. So I think it's probably come back to basics, right? So we look for a micro-LED package, right, that we can put on a PCB, okay? So this is what they spec and look for if someone can develop for us. Like, hey, we have like a 10 by 10 micro-LED in a small package with, I don't know, it depends on 0.2 millimeters, so about 2 millimeter by 2 millimeter, has 100 pixels in there. If you can develop that, and with that pad density behind that, in that geometry, the PCB can fit, then we can put micro-LED on FR4 PCB. And why not, right? So that's what we're doing today. It's really mini LED today, right? But if we can make a micro-LED today, we can make robust micro-LED display without that pixel. And it's more power efficient, and it can be repaired, no dead pixels. And most importantly, it can drive LED at nanosecond range, so very high dynamic range. TFT-based cannot, right? TFT just so slow. It cannot produce gigahertz clock, right? So this can, right? So, and we already proved that. So I look for partner to develop this package, whether academic or industrial. So this is the application Army lieutenant telling me. That's what we do a comparison in their shop. So our sample over there, that's what they're using today, right? Control the drone, so thin and so small. They want bigger, right? They want 13-inch, 4,000 nit, long battery power. So this whole thing should be like less than 5 watts for the whole display. Then you can carry for a long time, and they can visualize at bright sunlight, right? So that's important. And I think we are not looking for, particular fancy technology to make it too difficult to make, right? Make it easy to make and make it zero dead pixel, right? That's key, right? To make it as a reasonable technology that warfighter can use. So the other thing we're working on, actually with G1 and the MIT team here, to develop a product that directly mounting micro-LED on wafers, right? So I think that we're looking for 2 ways to do it and for different applications. So one will be still using a wire bond technology. You have a wire bond pump here. That probably for display or projection. We think we can use that. And the other way would be for AI communication that you need very high bandwidth. And you have to be like chiplet architecture. So that you need to have the TSV, through silicon via, as a communication. So that brings a lot of complexity, in terms of like electronics and IP, and also the cost, right? So there's like 5 nanometer or 3 nanometer IP available, but each tape out costs you $15 million, right? So it's difficult to afford that, and then, so we need to trade off like what application choose what technology, and technology means not just silicon, but also packaging technology that can be economical and also practical. So that's kind of 2 ways we're thinking about it in a different bonding method. So this one other case, we got requests from both from the Navy and the Air Force. They really need very wide range wavelengths from UV all the way down to mid-wave IR, right? So UV probably like less than 400 nanometer. Go to mid-wave IR, talking about 4 micron, right? So maybe look for this kind of a projection, right? To do it's almost like a AR or VR display, but it's a much bigger pitch. We're looking for 24 micron pitch, so about 1 million pixel. But key thing here is really how to get the mid-wavelength IR. So there's a professor over there talk about mid-wave IR. So I think it's very promising that MIT may have a solution for it. It would be good to have a total quantum dot solution, and then we can convert from UV to blue to near infrared and MWIR. So we need UV at micro-LED and MWIR. So that's what we're looking for partnership here, or cross-industrial partner. So another application we talk about is communication. People talk about communication, right, for AI. I mean, AI, as Professor, I forgot the name, say, is really the communication, right, between the GPU and memory. I think one of the key things here is that people right now, because the communication needs to be so close to each other, they developed a high bandwidth memory. Now, why is that? Because it has to be very short distance. If you have a longer distance communication with very, very, very low power and high speed, then you don't need to have your HBM. You can just use DDR, right? So we think using micro-LED to develop as a communication device has a great future and has an immediate need to reduce power and also reduce the cost. So if you have a computing can be located not just very close to each other, can be 10 meters away, the power consumption will be much lower. The cooling need will be much lower too, right? Right now, the data center, the liquid cooling, I think that huge power consumption and is too hot, right? So if we can come up a method using micro-LED as a very efficient and low-cost method to do the communication, will be much lower cost and lower power than laser. So I think that would be a very cool things to do. That's a challenge though. So this is what we are talking about using developing a chip, right, or silicon photonics product that has to be less than 12 nanometer TSV technology, right, whether TSMC, Intel, whoever, but it has to be less than that, so it can be a chiplet technology, and it be in UCIe 2.0 to be compatible to NVIDIA, Intel, or AMD GPU. So the target will be 1 picojoule per bit. It has to achieve that power consumption target. Then it'll be tremendously helpful to the power consumption currently it has now, because right now laser more like 10 picojoules, under 15 picojoules per bit. Right? So it can drop by 10x if we can convert it properly. So the problem is like, hey, we need high bandwidth LED, right? We're talking about at least 1 gigahertz. So we need a partner that really can do color frequency over 1 gigahertz. I think right now, a lot of display application, the color frequency is probably only 50 megahertz. So it's different application and a different device. So we need like very small input capacitance, right? And then very, very fast switching, at least 1 gigahertz. Then doing this way, we can use multi-mode fiber bundle, maybe about 1,200 of them, right? So the technology not super high integration. We're talking about only about 1,000 micro-LED, right? And then pitch probably like 100 micron, right, in that range. So, but the key thing is the efficiency and then the bandwidth. And also, we will look for a good technology partner to do the communication, developing in 12 nanometer. We don't want things in 5 nanometer because it's too expensive, right? So if there's an IP developer, can work with us to develop the UCIe interface, and then also high bandwidth LED, that will be awesome. So our business model is still like that. We are the driver maker, right? We always based on driver. We work with other people, to build a display or a solution, right? So that's how we position ourselves, and then and that's it. So we're a startup company. We are not exactly a startup. We are a small company, but I think our customers are not small. So we have a very unique IP portfolio. So we're seeking for technical partner to complete the team. Thank you very much.
Anyone have questions? What is the resolution?
Driver, I think, can go down to very small, can be go down 2 micron, even 1 micron, yeah. LED, yeah. How to mount it, how to make it efficient, how to make it high bandwidth.
I have a quick question. Yeah, during lunch, there was the question of, right, what is the priority of displays to the government? And it seems like you have a unique position.
Right.
Can you give some perspective of, what are opportunities to really solve problems that the government uniquely has with displays that are, unique capabilities within displays?
Yeah, look at this one, right? This actually is a demanding right now that it could be a reasonable volume too. You have a high brightness, low power consumption monitor, just tablet, right? But it has to be high brightness enough, and it has to be long battery. So I think OLED LCD just not there, right? I mean, look at that. That's LCD, high brightness LCD. It's just like too dim. And then there's particularly interesting if you can integrate IR into it. That'll be interesting too. So soldier can use it at night. Or, there's something called in Ukraine, right? The sort of a camouflage tank. So if you can do RGB and IR display in your display, you can help the soldier to identify the object. So there are kind of application with infrared if we can integrate it. I think MIT has a great technology here. They have an infrared QD, so I think that will be a good application for military. Thank you.
Any other questions?
Yeah, so just if you can maybe expand upon that. So yeah, I saw, UV pixels and of course, yeah. So it wouldn't be viewed by a human then. You're more looking at, ultimately it might be viewed by like another vehicle or something of the sorts.
Exactly. It's viewed by sensors, right? Viewed by MWIR sensors. It's like, I don't know, application, but it's like, something you could say anti-missile technology. When missile enter in the atmosphere, the temperature could be 1500 Kelvin. They radiate the mid-wave IR. So the thing is like, you're training the soldier or a pilot for their survival, right? So you imitate the pattern that missile when going through the atmosphere. So that's actually MWIR is particularly important for pilot for survivability.